Okay, so we skipped the discussion of what happens if there's a third factor this morning besides labor and capital. Let's call it land. Let's say we're thinking about natural resources, and to shorten that phrase, let's call it land. So we've got our production function in effective capital, labor, and land or resources. Now let's say there's a kind of sub-production function in labor and capital. So those compose to something you might call effective capital, if capital's the sort of predominant part of that combo. Rho y will denote that substitution parameter between labor and capital only. And for now, let's assume that it's 1. So effective capital and labor are perfect substitutes. Now, if there's no land augmenting tech growth, if V is fixed, and if the substitution parameter between land and the other factors, which we'll call rho W, if that's bounded below 0, then it's going to bottleneck growth altogether, right? Because VW is fixed, no matter how much AK and BL you've got, even if it's infinite, output's going to be finite. And if it's bounded above 0, we're in the gross substitutes case, land eventually becomes like water. In fact, water is an example of this, right? It's a natural resource that is so abundant that its share is minuscule. And even though we'd die if we had none of it, on the margin, it does not contribute further to growth, really. So the interesting case here with V fixed is going to be the Cobb-Douglas case, where land slows down growth a little bit, with that constant share. Now, if there is land augmenting tech growth, if you need less and less land or less and less resources to make effective use of a bunch of labor and capital over time, then the gross complements case will also be interesting between land and the other things. Because there's going to be a ceiling at any given point in time imposed by the amount of effective land you have. But that ceiling will rise over time with technological development, and you can get sustained growth. And so we'll talk a bit about that actually on Friday. But for now, let's just say you've got a Cobb-Douglas land constraint. All right? Okay, so basically this is our production function. Make sense? We've got that rho y equaling 1. So effective capital and labor are gross substitutes, and you've got an alpha less than 1, reflecting the fact that you've got decreasing returns to scale due to the finite resources. And yeah, let's suppose that, as we've been assuming, let's suppose that the AK can grow faster than the BL. So in the long run, effective capital is like 100% of I said it's like 100% of like this extended capital thing, the capital and labor. And so what this is basically the Solow model with a fixed population, except now it's not population that's fixed with the 1 minus alpha exponent. It's land that's fixed. So you've got technology, A, you could kind of pull it outside of the parentheses or not. This is Cobb-Douglas, so it doesn't matter. And you're going to get, given exponential technology growth, you're going to get exponential growth in output, and you're going to get a steady state capital to output ratio, because capital is just accumulated past output. So if output's growing at 10% a year, then the capital stock will also in the long run, given a constant savings rate, it'll be growing at 10% a year. And this will be the formula. The thing that makes GK constant, you perform our old trick. You take the growth rate of GK. So alpha GA plus alpha minus 1 G steady state K, that's going to be 0. And rearranging that, you get our steady state growth rates of capital and output equal to alpha over 1 minus alpha times GA. Got that? So we can get full automation and that capital augmenting tech growth. But just putting that little alpha less than 1 there knocks it down from double exponential to exponential steady state growth, just like in the Solow model. Okay? Do we kind of get that? Okay. I guess I accidentally changed the name of the label somewhere between last night and tonight and today. But so growth is going to be exponential rather than super exponential. It'll be an increase. I mean, you can just kind of see that because like alpha is going to rise because instead of just being the exponent on capital, it's now the exponent on capital and labor. And it could be huge, that increase. So, you know, right now, the natural resource share is like on the order of 5%. I think I mentioned this on, you know, over the weekend when I was talking about justifying the constant returns to scale assumption. You can look kind of like right now, what's the natural resource share? And, you know, let's say GA is growing at like, you know, 60 or 70% a year. That would imply a steady state growth rate. Yeah, it's exponential, but it's huge because the, you know, the land constraints slowing things down, but just barely slowing them down from what would otherwise be a growth rate that rose and rose and rose without bound. It's double exponentially. So yeah, 0.5 over 0.95 is, sorry. 0.95 over 0.05. That's alpha 1 minus alpha. That's 20 times 0.95. So it's basically 20. So if the capital's without the land constraint, it would be able to like almost double every year or something. Then the steady state growth rate is going to be like, whatever. It's going to like be 20 times that or something. Now, that won't happen all at once, right? We build the robots, but at first, that first robot's a really small share of people plus robots, right? They're only pulling up the growth rate of people plus robots after they've kind of accumulated. And so if you recall Nordhaus's projection, his was more conservative, right? He had a GA of 10%, and you know, but anyway, you don't snap your fingers and suddenly see the growth rate leap up. The growth rate rises, but if you wait long enough, it should rise far. We still see the labor share going to 0 here. Yeah, hopefully intuition's still pretty straightforward. The share going to labor and capital is going to be alpha, because labor and capital are just like, they're kind of doing the same thing, and the exponent on that thing is alpha. 1 minus alpha is going to the land. And of the people plus robots, an ever smaller fraction of them are people. Yeah, so labor share is going to 0. Any questions on that? As for wages, so again, think of the analogy to the Solow model. So basically, the marginal product of capital is going to stay the same. If there were no BL there, the marginal product of capital would stay the same because like the interest rate staying the same, you're getting this balanced growth where the marginal product of capital times the quantity of capital, which is like payments to capital, that's growing at the same rate as output, and capital is growing at the same rate as output, so the interest rate is staying the same. But here, what's sustaining that is you have AK, you have A growing, and if B is not growing, then each person is getting as much done as ever fewer units of capital. Because A is growing, if A is growing faster than B. So yeah, so the growth rate of the wage is just, it ends up just reducing to GB minus GA. It's kind of like, it's the growth over time of how many units of capital one person can take the place of. And that'll always be less than what GB was before, which was the old growth rate of wages. And it can easily be negative. In particular, it's going to be negative if we shift entirely from developing the labor augmenting to the capital augmenting kind of technology, because then you just have the minus GA, and that's negative. For the reason I was saying before, like each unit of effective capital is going to get the same marginal product, but then each unit of labor is going to count for less. Yeah. This is kind of another way to get to the intuition. You now have decreasing returns instead of constant in that sum. And so for the first time, accumulating AK is going to sort of crowd the Earth. So you're lowering the returns to well, both K and A, though for both K and L, but in the K case, that's offset by the fact that A is growing. In the labor case, without fast growth in B, you just have the crowding point, and so you're going to be lowering the marginal product of labor. An interesting exercise, which combines this point with the point we saw before about how when rho is less than 1, the increased quantity of capital raises the marginal product of labor. So yeah, combining these 2 points, let's say you have both. So let's say you've got this sub-production function that combines effective capital and labor. We're just holding B fixed, raising it to the alpha. But now this function has a substitution parameter that's not 1, as we've been assuming here, that's between 0 and 1. So now more capital lowers the marginal product of labor because of the alpha, the crowding, but it raises the marginal product of labor because inside the F, you have some complementarity. The question is when, if ever, is that complementarity going to be enough to, given that we stay in the gross substitutes range, when is it going to be enough to outweigh the crowding point such that this accumulation of effective capital actually raises wages? It's just going to be algebra, right? You're just going to like just have rho and stick it in here and take the marginal product of labor. And you'll see whether there is such a rho. But then, think about it. Think about the interpretation of what you find. More generally, the same thing is going to happen if you have a third factor that's not land, So let's say the, because the first thing I want to say is like, this point we saw before about factor augmenting technology always weakly raising the marginal product of the other factor, or increasing the quantity of one factor, weakly raising the marginal product of the other in the case of CRS and concavity. It turns out, as we've just seen, that result only holds when there's only 2 factors. If you have more than 2, the existence of a third factor can make it the case that making one of the other 2 more plentiful lowers the marginal product of the other. So you don't even need that point about how you can have, in effect, factor depleting technology that lowers its marginal product. You can have the coefficient, the technology coefficient on every factor rising or weakly rising, and yet the marginal product of some falling because some things are growing more plentiful faster than others, and the substitutes are growing more plentiful faster than the complements, as in this case. The capital growing faster than the land.
If I catch correctly, if there are 3 factors, we lose all the conclusions that we discussed so far.
Yep. You lose that conclusion, right?
Then how do we think about that? I thought that was a very strong conclusion of the family of models that we're considering so far.
No. So I was listing this as a reason why. Where is it here? I was listing this kind of mainly as a reason why some people think that wages aren't going to fall, and I mean, as I kind of put at the end, I think anecdotally this insight is part of why a lot of people, maybe especially economists, have the intuition that more stuff means more for everyone. And I'm just showing that that's kind of brittle. So one way that this can fail is just yeah, this is true if A or K go up and B and L stay constant, but B can just fall because you can just have a change in the shape of the production possibilities frontier that increases output, and it ends up in reduced form. It ends up being a lowering of B. That's the one way this can be wrong. The other way this can be wrong is there can be 3 factors, and if it's wrong, then you lose its conclusion. So it's a weaker conclusion than some people realize for both reasons. Yeah. And then, I was saying this is going to be true for third factors more generally. For instance, let's say W is high-skilled labor there's some skills some people just can't acquire, or it would take a long time or be really costly for them to acquire or something. And L is the low skilled. If like the robots can substitute for the high skilled but not the low skilled, then wages can fall for the low skilled, right? And we've seen this in different contexts many times now. But yeah, this is like the case of the immigrants that are all plumbers or something. Okay, so that's all about third fixed factors. Any questions on that, or should I move on to the heterogeneous? Good. Question, yes.
Are produced with a third factor. This will slow, like bring down the growth rate from super exponential to exponential, right? So if we have this isoelastic.
Yeah, I think maybe the key isn't the isoelasticity so much as the gross complementarity. If output is a gross complements combo of lots of tasks, and even one of those tasks requires natural resources that are in fixed supply, then output will be bottleneck.
I guess there's a reason.
I'm not an expert on this, and people definitely debate it and have different intuitions. Like I was saying at the beginning, I mean, some people, some kind of more from the environmentalist community will say that, lots of things we still don't know how to make in a way that is not depleting some necessary environmental resource or something. And so, yeah, it's true that like the natural resource share is really low, and even for the particular goods for which it's high, I think on inspection, it kind of seems like we could do it in a much less resource intensive way. It's just that it would be costlier. But if we were way richer, we could just, build loads of solar panels and like giant batteries that aren't very efficient. But we could just like stack big, blocks on top of each other in the desert and then have big pulleys that, like, we have, there's a way of looking at it, which we'll talk a little bit more about maybe later, that on some level, maybe energy is kind of all you need, and we know how to make and store energy in a way that's not very resource intensive. But again, I'm not an expert on this, and if you believe that there's some necessary kinds of production which properly accounted for are really resource intensive given current technology, then I can't argue with you. Does anyone have a better informed take on the extent to which natural resources will be a bottleneck to growth in the long run?
Yeah, absolutely. I guess AI will lead to super exponential growth.
Absolutely. No, it's absolute. That's a great point, and that's actually something that will come up explicitly on Friday. Yeah, that would be a case of rising V. V was the technology term on resources, on land. We don't need as much to create as much output in some sense. Okay. So something I should have mentioned when I was going through those Nordhaus slides is that when looking at the capital share over time, labor productivity and so on, those numbers were all up to like the end of 2024 in most cases, or even the beginning of 2025, or at worst the end of 2023. So I updated them. I wasn't just using the ones he published in 2021. And I extended them in a few ways. I added some new series, as I mentioned. Here's another thing that I think might be worth keeping track of, but which takes heterogeneity in output more seriously than the series that we looked at this morning. It's what you might call the network adjusted capital share for particular goods. What is that? Well, if you trace back $1 spent on some product, say a robot, all the way back down the supply chain, what the network adjusted capital share is how much of it is paid in compensation for value added by capital, as opposed to by labor. This could be relevant for a few reasons. First, the economy-wide capital share could be a lagging indicator of like some trend toward full automation. If we were getting close to kind of making that first closed loop of a supply chain, so where you just didn't need humans in the loop. Let's call that a little bit tongue-in-cheekly a self-replicating robot. If you were getting close to making it, but it hadn't yet become numerous, the labor share would still be high at the moment, but you'd easily be able to predict that it was going to fall soon, because the robots will just become more plentiful and they'll be able to do what we can do. Could also be relevant if you think we might be in something like that sort of knife-edgy case I was laying out, where consumption is like this Cobb-Douglas combo of capital and labor, but the capital doesn't need labor to increase. If you're just looking at the Nordhaus things, you're looking at the capital share over time, you're like, oh, that's still 0.4 or something. That may be because people are necessary to create like those final consumption goods, but we're still going to get a growth explosion soon because like we're kind of about to close the loop on the K production. And then finally, yeah, self-replicating machines could be worrying even if they're not broadly economically useful. If we have no human in the loop, rapidly spinning assembly line for drones or something, that'll just kind of be geopolitically relevant. Okay. So Bakke in 2015 introduced the notion of a network-adjusted labor share, or factor share more general. Here's how you calculate it. The US Bureau of Economic Analysis and people doing similar work at the OECD and other places, every year or a few years at different levels of specificity come up with what's called a use matrix, which has, it's like a square with a row and column for every industry at some level of granularity. And what a column I is telling you is for each dollar of revenue received by a firm in that industry from selling the kind of output that industry produces, how much is spent on intermediate inputs from industry J, for row J. That make sense? So Starbucks sells you a coffee, so you give them $5, and some of it goes to the employees as wages, to the owners of the Starbucks company as sort of returns on the capital of the company that they own. That's called profits. And some goes to the state in taxes. But the rest will go toward the people who send them like the beans and the landlord if they don't own the store, and the electricity for the lights in the store and all that. So typically these columns will sum to less than 1. They could sum to more than 1 if they get negative tax, if they're massively subsidized and that outweighs A and B. So let alpha K be the vector of this fraction of every dollar that you give Starbucks that the owners take home as profits. So it's profits divided by revenue. This doesn't mean or, this is divided. So profits divided by revenue, that'll be the profit margin. Alpha L be the fraction that goes to wages, just at that firm, not down the supply chain. And alpha G be the government's share. And here, yeah, you can see that for each I, for each of those columns, the sum of the use matrix down the rows plus the fraction that goes to capital, labor, and taxes has to be 1. See that? For every dollar they take in, it's going somewhere. Yeah. So let V be the column vector with a 1 in the row for, say, the robot industry, and zeros elsewhere. So UV just picks out the column, like the Vth column. So it's telling you the vector of first order, like first step inputs. This first order, I don't mean like a first order approximation. I just mean like the vector of inputs after one step to robots. It means for every dollar you spend on robots, they spend 3 cents on, whatever, this kind of ore, and then 5 cents on this, and 20 cents on electricity. So We get what UV is. You've got your matrix, and then V, UV is going to be the vector of inputs. And so U times UV is going to be the vector of like inputs to the inputs, and so on. Maybe I should write this down. So this is U. And then this is the robot column. Whatever. This will add up to something less than 1. V, I'll put up here. If y'all don't know this trick, I just think it's just very helpful. So I'll share it now. When you're multiplying matrices, or matrices and vectors, put the one on the right up here so that you can, when figuring out what goes in this entry, it's going to be the dot product of like the row to its left and the column to its right. Okay, so V has zeros, let's say, in all the other entries, but it's got a 1 in like the third entry here because robot's the third column here. So this is going to be UV. It's this vector. And that's just this column. And then if you want to say, okay, of that dollar I spent on the robot, how much of it is spent on, let's say this is electricity. This is a little low, but let's say only 3 cents get spent on electricity. Well, 3 cents get spent by the firm where I bought the robot. Like it takes 3 cents and it spends it on electricity, but a bunch of its other spending goes to other firms which are going to be buying electricity. So how much goes to electricity once you take that into account? Well, take U here, and then put UV up here. And then you're going to have like this dot product. You're going to look for every penny that industry 1 gets, it spends a certain amount on electricity. And for every penny that industry 2 gets from that first firm, it's also spending some of that on electricity. So this dot product is how much is spent on electricity by all the firms creating the intermediate goods that are bought by the firm that you bought the robot at. Okay? And then what about all the firms making all the intermediates that the firms making the intermediates make? Well, that's going to be U times UV, and so on. And the way that series sums, you take, just like with, 1 times a half, 1 plus a half plus a quarter plus an eighth, and so on, being 1 over 1 minus a half, so 2. The same thing works for matrices. So that's the identity matrix. This is U. The identity matrix is, it's going to be the same dimensions, and this minus that inverse. That's like 1 minus a half, like 1 over 1 minus a half. So, and then, so this times the vector that had the 1 in it for the robot entry and the zeros elsewhere is going to be called the vector of total requirements for robots. And it says if you trace the dollar back all the way down the supply chain, sort of infinitely, how much ultimately goes to a firm in industry 1, electricity, industry 2, hammers, industry 3, whatever. Get that? Now, technically, it doesn't tell you if you buy a robot now. I guess I'll get to this. Yeah. So far, in a static economy, this is how that would work. Yeah.
This is the dollar value.
Yep.
And it still comes.
No.
And so it could be I guess empirically it would be infeasible for some goods that we already produce.
What could be infeasible?
The cost or like the total volume requirement of inputs for the final good that we produce and sell.
Oh, I mean, it could add up to more than one? I mean, one way it could add up to more than one is just like the initial firm could be like getting a subsidy for every unit it sells. And so it gets a profit, its employees get paid, and it buys a bunch of intermediate inputs, which themselves add up to more than one in dollars, right? And so even that first UV could be could add up to more than one. And then even when you add up all the rest of it, that could easily add up to more than one. In fact, it'll often add up to more than one because you're in some sense you're sort of double counting. Like the same dollar that gets passed around gets added every time, which is possible without any subsidy. Yeah. Okay. And then the network adjusted capital share is the fraction of all, like once it bottoms, because every time a dollar passes through a firm, some fraction of it gets skimmed off for capital, for labor, and for taxes. Okay? Like once, like you have this vector of first order inputs, and you can say, okay, like what this matrix is telling you is like how much they all spend on electricity and how much they all spend on the next thing and how much they all spend on the third thing. But they don't take every dollar they get and buy intermediates with it. In fact, if they did, that series wouldn't converge. They're also going to be taking some of it out as profit or paying some of it out as wages. So you can say, once we've got this vector of total requirements, just dot product it by the vector of capital shares by industry. And that's the fraction of the dollar that you spent on the robots that gets received as profits by someone all the way down the supply chain. You can define the network adjusted labor share likewise. Now, those two things will typically add up to something less than one due to taxes. As I was saying, it could be greater than one if there are subsidies. But I think we probably don't want to say that a human-free supply chain is only partially automated because of taxes. So let's define the network adjusted private capital share as the network adjusted capital share divided by the sum of the network adjusted capital share and the network adjusted labor share. If some good has a network adjusted private capital share of 1, that means everyone in the world could die and it would just go on multiplying. Right? Because at every step on the supply chain, people aren't adding any value. At least if people are being paid for the value they're adding. And it's not necessarily true if there are like non-automated public services that are necessary. So that would kind of be a reason to include taxes in the numerator. But I think in general, it's not like how much public services are contributing to a given firm is reflected in how much they're paying in taxes. Like that's the whole point about public services. They're public goods. You're not like paying for them piece rate. So I think this is probably a more helpful measure. So this network adjusted private capital share would capture where each dollar kind of ultimately went if we were in a static economy. But actually, it captures something even more relevant, which is where every dollar spent on coffee or robots or whatever would go today, given today's supply chain. So let's say it takes 2 years to build a robot from scratch. And last year, we couldn't automate some of the steps, but now we can. So let's say, some electricity was used last year. And back then, we needed human electricians. But by now, we've automated that. If you're just inverting the matrix as it looks this year, then you're saying right now, if you started today, building a robot, or if you spent $1 on a robot today, to pay back all the value added from building a new robot starting today, how much would be received by capital and how much would be received by labor. And so that'll be one today, even if in fact all the robots like sitting on the store shelves today had some human input in them because they were partially built last year before we had automated electricity. Does that make sense? Okay, so this is just as flat as a board. There's just, I thought maybe we'll find some interesting trend or something, and it's just way flatter for particular industries even than the aggregate share is. And so yeah, I just picked out 3 particular industries: computer and electronic products. Well, actually, yeah, one thing was computer and electronic products measured 3 ways. And you can look at semiconductors in particular, and that's only measured every 5 years. So the data is kind of lagging, but that's also flat. You might also be interested in like what the maximum is over time, because it's just like, well, how close are we to making that first fully automated supply chain, whatever the product is? But that's actually, it's usually crude oil. So it's not really that it's almost automated. It's just that like almost all of the dollar that you spend on crude oil is just received by the owner of that natural resource. And because the accounts here don't separate accumulable capital from natural resources, that ends up being reflected as a high network adjusted capital share or private capital share. At first glance, this seems sort of surprising maybe if you kind of look at how high the capital expenses are at a place like TSMC. And the resolution to the puzzle is that the supply chains are really long. So yeah, at a given firm, like if you're buying a chip from TSMC, they are only getting a tiny fraction of that as wages. And as far as TSMC is concerned, on their balance sheet, they've got these huge capital expenses, right? In fact, the profits that you get from owning a share of TSMC aren't even, those are profits rather than capital expenses as far as TSMC is concerned. It's the intermediate inputs that are the capital expenses. And those are huge, right? But if you've got a really long supply chain with like 50 steps and labor is just skimming off 1% at every step, right? Then you have a network adjusted capital share of like 50%. And because of all the mixing between industries, the industry specific numbers tend not to be that far from the aggregate share, with some outliers like crude oil. Yeah. Oh, yeah.
I think that sort of answers my question. I guess the casual understanding is that the capital share has been rising in manufacturing.
Mm-hmm.
The growth of services in terms of share of overall economy is what's preserved the overall labor share.
Yeah, yeah.
And so I guess this is saying that when you do the network adjustment, you're sort of taking some the other sectors that.
Yeah, yeah. It's a great point. To fully reconcile them, you would need to think that there were some kind of service sector industries that were like that were somehow important inputs to what we've been thinking of as manufacturing, like consulting or something. Yeah. I haven't actually done any sort of accounting to see how to fully reconcile these facts. I've just dug into this network adjusted capital share thing and found that it's like pretty flat across industries, which I agree at face value. Like logically, you could reconcile them in some way like this, but it would be a totally different story from what we normally think of, where we're switching from widgets to massages or something. Like massages aren't like deep in the supply chain for widgets. Yeah.
But look, just from 2001 to 2015, there's like roughly a 10 percentage point increase, which is basically what the change in the aggregate labor share is.
Yeah, but you're picking the lowest number, 2001.
Yeah, but I think this is a problem with the way people talk about the labor share trend over time.
Oh, yeah.
From that lowest point in 2000.
Okay. I agree with that people do overstate the rise in the capital share to begin with. Okay, interesting. I hadn't noticed that. Okay, Caldor facts for the win. All right. So now we'll think about heterogeneous output more, I don't know, more fully. So, because this was just heterogeneity in the sense of like, well, at least the motivating example for this was just kind of like robots versus everything else, right? Or like capital versus consumption. But obviously there are heterogeneous consumption goods as well. Let's say, okay, right. So by analogy, recall the definition of TFP growth when you've got, capital and labor as production factors. The definition is that it's a share weighted average of the growth rates of the two kinds of factor augmenting technology. And something we saw, if you remember, is that you can define TFP growth that way. And if you do, there's going to be a variable. It's sort of a weird construct of a variable, but there is a real thing, a variable that grows according to that growth rate. So if you're figuring, you can put a number to it and say how much bigger is it now than it used to be, and accumulate it over time, and it'll behave sensibly. And that's what it'll be. It'll be labor augmenting tech to the capital, capital augmenting tech to the capital share times labor augmenting tech to the labor share. Given to consumption goods, say, let sigma denote the GDP share of good 1. What we do is we define real GDP growth analogously. We say it's the share-weighted growth rate of the quantities of the two goods. I think this is a more straightforward path to seeing what real GDP growth is defined as than the way it's sometimes introduced, where you talk about nominal GDP growth and then you deflate it by a price deflator. You don't need to get into prices at all. It ends up reducing to this. Real GDP growth is the share-weighted average of the growth rates of the quantities of different goods. This is the kind of standard, chain-weighted definition of real GDP growth in continuous time. And you can do the same thing when measuring other aggregates like consumption or capital. Obviously, we can't measure this in continuous time exactly. In fact, it's not really defined in continuous time. It's not like goods are being consumed. Like you buy things now and then when you go to a store, But in principle, this is the thing that we're trying to measure when we're trying to measure real GDP growth. And to the extent that we're not getting that, we call that mismeasurement. Okay? So that's real GDP growth. Something I think is just like crazily underappreciated. It's not like I'm the one that first noticed this or anything. You can goes back to this guy Dewart and the first people thinking about index number theory and so on. But something Chad Jones didn't know, and I'm sorry I'm being recorded, but you have one job, like okay, but is that this isn't really even a quantity unless people have homothetic utility that's the same across the population and constant over time. More precisely, there's going to be no homogeneous of degree 1 function of the goods that always grows according to this formula for real GDP growth. You probably want it to be homogeneous of degree 1 because you want to say that if there's two countries side by side and one of them's producing twice as much of every single product, its GDP is double that of its neighbor. There's an example I'll rush through, but you can come back and look at it in more detail if it's helpful, for kind of what the issue is. Let's say people have these utility functions that are really concave in one good and linear in the other good. So, utility in good 1 is just a line, and utility in good 2, like utility in good 1 and then utility in good 2, and utility in good 2 is like that. It's like -1 over good 2. So prices are proportional to marginal utilities. So the GDP share of good 1 is like its price, or its marginal utility times its quantity divided by the sum of prices times quantities. Let's say we start out with only a tiny bit of good 1 and 1 unit of good 2. 1 unit of good 2 is where its marginal utility equals that of good 1. This slope is always 1. This slope is 1 at 1 unit. Okay? So we start out with their marginal utilities being equal, but the quantity of good 2 being 1,000 times higher. So the share of good 2 is going to be 1,000 times higher. Make sense? So we start out with an economy where the GDP share of good 2 is basically 100%. And we'll consider two possible growth paths. On one, both paths last for 2 periods. And on the first path, we continuously grow the quantity of good 1 at a constant rate such that we have 1,000 times more of it in that intermediate period, period 1. So we have 1,000 times more, so at the end of it, we have 1 unit of each, right? And the shares are 50-50 because the prices are the same. The quantity, the quantities are the same. And in that first period, the quantity of good 2 is not growing. And then we, for the second stretch, we do the opposite. We keep the quantity of good 1 fixed at 1 unit, and the quantity of good 2 gets multiplied by 1,000. So we have 1,000 units at the end. So that's the first growth path. We first grow good 1 up to 1 unit, and then we grow good 2 up to 1,000 units. And the second path is that we first exacerbate the difference in quantities by having good 2 go from 1 unit to 1,000. So now there's 1,000,000 times more of it. And then we grow good 1. So then there's 1 whole unit of good 1. On both paths, the starting point and the ending point are exactly the same. I said I would go through this quickly. Now I'm really just going through it. But anyway, at time 2, you have 1 unit of good 1 and 1,000 units of good 2. And so these subscripts are time. So on both paths, the share of good 1 at time 0 is around 0. And the share of good 1 at time 2 is around 1. The reason it's around 1 is that the price of good 2 is basically nothing once it's gotten really, really plentiful. But on the first path, the share of good 1 is a half in that intermediate period, whereas on path B, the share of good 1 is basically 0, right? There's 1 unit of good 1, there's 1,000,000 units of good 2. Anyway, it turns out that on the first path, y2 is 2 of y0. Like if you just integrate the growth rate from time 0 to time 2, real GDP doubled on this first path. But real GDP got multiplied by a factor of 500 on the second path. Neither of these paths has it growing by a factor of 1,000, which is what homogeneity of degree 1 would require, because the quantity of both gets multiplied by a factor of 1,000. But yeah, you can look in the appendix for the calculation. But like the reason is that you set things up so that good 1 is growing on path A while it's still a small share of GDP. And then good 2 grows, but while it's growing, it's becoming a small share of GDP. So the fast-growing things are just always small shares of GDP. Whereas on path B, it's the other way. Good 2, which starts out as a big share of GDP, you make that grow, so it counts for a lot of GDP growth. And then it grows so much that its share falls to 0. And now that little bit of good 1 you have, that's back to being a decent share of GDP, and it grows by a factor of 1,000 while it's a large share of GDP. And in fact, the general result is that as long as you deviate at all from that assumption of completely homothetic utility that's the same across a population, constant over time, you can have any initial and final distribution of goods across people, including the same distribution at the end of some stretch of time as at the beginning. And there's a consumption path between them such that real GDP growth is any number. For any number you pick, you can construct a consumption path. Yeah. So real GDP is not a quantity. For example, speed's a measure of location change, but unless you're always running in the same direction, integrating your speed over time gives you no information about how far you are from where you started. You could have run in a circle. This is, yeah, what makes it a quantity is an unrealistic assumption. Yeah, typically, when thinking about growth, we just assume that there exists the kind of aggregation that you would need for growth to be well defined. Anyway, let's take a 15-minute, let's take a 12-minute break, and at 3:20, start talking about what Nordhaus has to say about heterogeneity. Yeah. Yeah, something I maybe just, I said usually here, and there are lots of exceptions, and there's ever more exceptions over time. I don't mean to like ignore all of that, and indeed we'll talk about some of it later. But I would just keep an eye out for it. Often things will be set up in a way that implicitly assume homotheticity, because it just makes things so much more complicated not to. Okay, so let's say everyone has a common CES, and so homothetic utility function over two goods, and as the substitution parameter is rho. Yep. Yeah, I mean, so I've got my favorite way of tracking utility growth with non-homothetic preferences. The standard thing is not, or not the standard thing, but there's like a family of things people do, which are not what I would have wanted to do, which are to, like you can look up this paper by Bakke and Burstein from 2022, in which they try to actually like model like what our utility functions are, right? So they're not like, yeah, they're building in room for non-homotheticity through like particular channels, like maybe as the population's aging and old people like different things and relative to young people, and so they have that like they write down that what they think our preferences really are, and then given those and given how the quantities of the goods that we've been consuming over time have been changing, you can ask, okay, what happens if we put a number to like how much we've grown? What that number is how much would people's budgets have to shrink today to make us all indifferent between life today with the smaller budget and life in the past as it actually was? And then you can compare that number to the number that we get for real GDP growth by chain weighting. And they find, over the course of like a generation or so, the numbers will diverge by, I don't know, 20% to 30% or whatever. I think they'll diverge ever more over time. And they won't be reversible. So the number of extra dollars you would need to give someone in the past to get them up to today's indifference curve will be different from the number of dollars you would have to take away from someone today to get us down onto the old indifference curve. And I'll explain why later. So there's all kinds of ways that this sort of calculation will be a little janky, but that's one thing you can do. There's a bunch of adjacent things in that spirit. Maybe we can talk later about what I would want to do, which is like I'm working on a paper with Chad on this stuff, and so I think there's more to say. But okay, so but when Nordhaus is thinking about what the fact that there are different goods that we have, different preferences over, what that might imply for what macro data have to say about whether we're anywhere close to explosive growth from automation or IT. This is what he does instead. He says, let's say we have that common homothetic, in particular CES utility function, over 2 goods. Substitution parameter is rho. Let's say our productivity at producing good 2 is growing exponentially, and our productivity at good 1 is fixed. So you could think of our production constraint at some time as taking that form. You've just got like a linear production possibilities frontier, but that triangle is getting stretched out. You know, it's like doubling every period or whatever as good 1 gets ever cheaper, ever easier to make. Now, in the Cobb-Douglas case, the GDP shares are going to be fixed, right? So each halving of good 2's, oh, sorry, I said good 1 was getting, yeah, sorry. This should be y2t over at plus y1t equals 1. So each halving of 2's relative price doubles the relative quantity that we produce or consume. So the price times the quantity is staying the same. And the amount that we're spending on good 1 is going to be fixed. So, let's say it's 50-50. The growth rate of GDP is just going to be half the growth rate of productivity at good 2. Right? Share weighted average of 0 and GA. So it's going to be the share times GA. But if the goods are gross complements, you get Baumol's cost disease, where as the technology improves, our share, oh, this is a problem. I tried changing it to good 1 to be consistent with the thing before. So this is the share of the good that we're getting more productive at. So this should be the share of good 2. Or if this equation stays right, this is a share of good 1. But this should be each halving of 1's relative price. So productivity at good 2 is fixed. It's good 1 that we're getting better at. That's probably the way to think about it. Corrective in that direction. So in this case, because the share is not fixed, the share of the fast-growing thing is falling to 0. The rate of GDP growth is just going to be some fraction of the well, it was all some fraction of GA. Anyway, you get Baumol's cost disease here, where output growth should go to 0 here, right? Oh. All right. Well, output growth should go to 0 here, and I messed that up. I'll work that out and change the slides later. And on the other side of the coin, if the goods are gross substitutes, then even if the good we're getting more productive at making starts out as a really tiny share of the economy, it's like chips. So yeah, productivity is really, really high for chips, but that's not contributing much to GDP growth because its share is really low. Its share will rise to 1 over time as we end up kind of shifting over into the thing that we're getting more productive at. You might call that Baumol's cost euphoria. Here, the growth rate of output will rise to the growth rate of our productivity at making the that one good. And the quantity of capital might accumulate as well, but the way I've just set this up for simplicity is that you're subjecting our purchases to an aggregate budget constraint of 1. So the lesson he's exploring here is that to drive explosive GDP growth, the AIs and the robots actually don't have to be able to produce everything. They just have to be gross substitutes in the production of some set of goods for which all other goods are gross substitutes in consumption. Does that make sense? Like, remember the mushroom pizza example? If other kinds of food are gross substitutes for mushroom pizza, yeah, once your robots are gross substitutes for labor in the production of everything else, you get your explosive growth. So the thought is, well, maybe the chips will eventually be gross substitutes for everything else. And a kind of comical, simple way that could happen is if we just kind of really fall in love with our video games. We spend all our time in ever more elaborate virtual worlds or something, and then that's all that the AI is making, but that like kind of comes to dominate GDP. So you just need them to be substitutes for that set of goods. And of course, for there to be a lot of capital or under this constraint, a lot of capital augmenting technology. So gross substitutes and large quantities. Nordhaus considers whether we, in fact, currently seem to be seeing gross substitution on the demand side between the goods and services produced by IT capital, like video games, and everything else. And he finds basically no clear evidence. For some goods, the falling relative, for some like IT goods, the falling relative prices over time have coincided with rising shares, which suggests a local elasticity of substitution greater than 1 positive substitution parameter. So those are the cases where the prices come down and the share's gone up. But for others, you've seen the reverse. And in fact, you really, I think, shouldn't extrapolate from even the cases where you see things looking gross substitutable, because that's just a local estimate. And indeed, whenever a new good is introduced, the price is going to decline. In some sense, it started out infinitely expensive before you could buy it for any price. And its share is going to rise from 0, because you're not buying any before it's introduced. So you're always going to get this gross substitution, or at least this estimate of gross substitution, for new goods. That just has to be the case, sort of, mechanically. And usually this trend is not sustained. Eventually, we start running out of good uses for the good, and as its price further declines, its share falls. So you get a sort of hump where the share starts out 0 before it's introduced, and then it gradually rises, and then it falls again. Talk about that a bit more soon. But before that, Zach will tell us about some work he's done actually tracking how big of a deal the Baumol effect has been historically. Because this is like a very common objection to the idea of explosive growth from AI. Like maybe it'll do all sorts of things, but we'll be bottlenecked on the other things. And so just seeing how strong an effect that's tended to be.
I don't know if you want to.
Yeah, Maxi, sorry.
Like if you want to provide a model, a task-based model that kind of includes this,
Yeah.
Is there some standard approach how we think that this substitutability evolves over time?
Yeah, it's a good question. The standard approaches that I always see are to either just assume gross substitution, period, for the new things, right? So in an expanding varieties growth model, where over time we can develop new things in addition to increasing the quantities of the old things, by far the standard assumption is that all the new things are just gross substitutes down the line, right? And that would imply that as if we introduce them, we keep getting cheaper at making them, that eventually they'll dominate GDP. At least if we don't get cheaper at making the old stuff. It also implies that because they're all gross substitutes, we can make up for a lack of those new things if we just had enough of the old things, right? And as with my rant about the horses, I think that just can't be right. You can get on a higher indifference curve when you develop new things sometimes. But anyway, that's one thing people very often do. Another thing is to just not make functional form assumptions and just have a really like a bunch of Acemoglu papers, Acemoglu and Restrepo and so on, will have much more flexible models in which there'll be some set of assumptions that guarantee nice behavior on the production function, including over like new tasks for people or new goods. And when you think about what those, why you need the assumptions you need and sort of what's driving them, at least part of the ingredient, like what exactly you need will depend on like how it's embedded in the context of the paper and so on. But ultimately what you'll kind of be needing is gross substitution at small quantities and gross complementarity at large quantities, or at least the option for it to become gross complementary at large quantities. And my kind of, I guess, sort of cheating because it's not really the workhorse model because it's just, but what I think would make sense would be to say, yeah, let's say you've got like this, good by good. You have this Kara utility function, which means when the quantity is small, you're around zero. The elasticity of substitution across goods is like as high as you want. It's like infinite if you're intersecting the axis at a positive slope. I mean, at a finite slope, right? Because at small quantities, it's like linear. They're perfect substitutes. And then as the quantities get large, you have a kind of upper Inada condition on the elasticity of the inverse elasticity of substitution. It goes to zero. Inverse elasticity goes to infinity. So, and in my playing around with these questions, that just is a really simple functional form that kind of does everything you want. And so that would be my recommendation.
All right, this is my big contribution for today, which is 4 slides. So yeah, the idea is just measuring the strength of the Baumol effect historically, and I did this as an exercise with my co-author, Basil Halperin. There are some other papers that have done this. I think the idea of how to do the decomposition comes from this Nordhaus 2001 paper. And the idea is you're measuring the Baumol effect relative to some reference period. So you hold industry value-added shares, like Domar weights, fixed at a base year, and then you calculate you look at what aggregate TFP has been, and that is equal to what aggregate or what TFP growth has been in each industry times their initial weights, their initial Domar weights, their initial value-added shares, plus just the decomposition terms of how those weights have changed over time. And the idea is this is the pure productivity term because it's saying if the shares didn't move around over time, so if we were back at our 1945 industry structure where services were a smaller fraction of the economy, how much growth would we have gotten? And the Baumol effect is the difference that comes from the shares changing over time. The input allocation terms thing you can basically ignore, but part of the contribution of the exercise we did is in the way the national accounts are measured, they assume that there's no profits in any industry, but we have reason to believe that like average markups in lots of industries are positive. If you account for that, you get some other terms, but we're going to ignore that for today. Cool. So the results using this BEA BLS integrated industry level production accounts, which go 1947 to 2016 in the US, and the initial weights for like the starting economy, which is our reference economy, are the average of industries value-added shares 1947 to 1952. The profit adjustment we do is this accounting profits approach, which follows Baki and Fari. Feel free to ask me more questions about that if you're interested in it, but I'm not going to focus on it because it's not really relevant to what we're getting at. Anyway, the results are, so like aggregate TFP over the full sample growth is 0.575 percentage points a year. The pure productivity term is 1.04 percentage points per year, while the Baumol effect is negative 0.28 percentage points per year. And we kind of split the data pre and post 1973 because a lot of times that's used as the year at which like productivity growth started slowing down. And you can see that 24% of the post 1973 productivity growth slowdown is due to the Baumol effect. The Baumol effect was dragging on growth before 1973, but it's dragged on growth significantly more since then. If we'd had no Baumol effect the whole time, so we'd somehow maintain those fixed shares from 1947 to 52, TFP today would be 35% higher, which is, a pretty good amount. 35% is a lot, but it's not all of it. And another curiosity is we were kind of trying to think about how much of the productivity growth slowdown is due to Baumol's cost disease versus ideas getting harder to find. You could think that the pure productivity slowdown from pre-1973 to post-1973 is something like ideas are getting harder to find. Baumol's 24%, but most of it's the pure productivity growth slowdown. Yep.
I mean, I think the biggest ones are different manufacturing industries, like cars or something, motor vehicles. But it's like, I think it's more the story about, the story people oftentimes tell is it's healthcare and education growing in weight, and though neither of those are industries in which you have much productivity growth. Energy also shrunk as a share, like Phil's earlier thing about it, the quantity staying constant, but the price has fallen. Yeah, so I think that gives us a sense that like the Baumol effect can meaningfully affect growth, like quite meaningfully, but it's not necessarily a huge effect that we really expect to bottleneck growth. Then there's, this is just a diagram. So the dark line is what TFP growth is under this measure of profits. Confusingly, I'm showing you two different ways of measuring profits, but just focus on the blue lines. This is like what TFP growth was, and then the dashed blue line is what it would have been if there had been no Baumol effect. So we see that the Baumol effect like matters a little bit pre-1973, but really matters since then, much more. And then there's this other paper, which I think is cool, Dornecker, Hannerendorf, and Valentini. They're doing a similar sort of exercise, but they split so they model the economy as a nested CES or a CES over goods and services, but then services are themselves a CES over progressive and stagnant services. And also, this is a form of non-homothetic CES, so it's not like the standard CES we've been seeing. And they split services into progressive and stagnant services, just arbitrarily based on whether they're above or below average post-war productivity growth within services. What this figure on the right shows is that the relative price of stagnant over progressive services increased over time, the blue line, but the value-added share is basically flat after rising a bit pre-1970. And this is an interesting pattern because if you thought, oh, like the stagnant services are complements with the progressive services, when their price is rising relative to the progressive services, their value-added share should as well. The fact that we don't observe that suggests they're substitutes, but the fact that the price is rising and the share's not falling means there has to be an income effect as well. So the way you can reconcile all of it is that stagnant services are a luxury good in the sense of you want to consume more of them as you get richer, but they're also substitutes with progressive services. And this gives a slightly more optimistic picture about future growth, since if these progressive and stagnant services are substitutes and progressive services keep growing, we'll be able to not get bottlenecked by the stagnant services growth. Yeah, Thomas. If I'm understanding what you're saying correctly, like you're wondering, could the J curve explain some of the fact that we've had lower productivity growth recently, and therefore this actually be about that rather than anything else? It's an interesting idea. I mean, I think it requires thinking that the J curve effects are like more significant in the more recent periods, which I'm not sure we have reason to believe that. Like part of Eric's point was there's like always different J curves going on. So I don't know that we should think the more recent period is more significantly overstated GDP growth relative to earlier periods. I also would say that the Baumol accounting exercise where you're just fixing the shares, that still shouldn't really, I mean, unless you think systematically the industries that were getting bigger are ones where we were also undercounting their intangible investment while the opposite holds in the industries that were getting smaller. Like you could tell a story like that, but I don't think that's what's going on here. Yep. Well, okay, you're saying you think those sorts of services are luxuries. So I think the reason the data tells you they're not is if they were both luxuries where you had like roughly equal preferences. There were like progressive and stagnant services were luxuries to the same degree, and the price of stagnant services is rising relative to progressive services, then you would expect that you're substituting, if they're also substitutes, you would expect that the value-added share of progressive services would rise over time, because you care about both, but one, you're willing to substitute between them and one's getting cheaper. The fact that the value added share is flat tells us, I actually think in the data, it's not necessarily that it's a necessity while it's a luxury, but that stagnant services are more of a luxury than progressive services. I don't remember the exact industries, but I'm almost positive healthcare, education. I mean, they're looking at the 63 industry levels. There's lots of others in there. I think real estate, like housing services, is a stagnant service. But I don't remember the exact other categories. If there's no more questions, we're going to go back to Phil for new goods.
Thanks. Yeah, just briefly, let me say about that in the spirit of new goods. A slowdown in TFP could totally be welfare increasing, right? It's not what you would have. It's not like can't happen in the homothetic case, but if your preferences are the ones that I was working through before, when I was kind of just introducing why it's so common to assume homotheticity and what goes wrong if you don't. Let's say that's your utility in good 2, and your utility in good 1 is linear, right? It could be that we're growing at like 5% a year in manufacturing, right? And then we've got this luxury where we switch over to services, and even though this is only growing at like 1% a year, we want this shift, right? So it's not necessarily a problem that we've had this slowdown in TFP or GDP growth or whatever. Okay, yeah. So as came up way back when I was just first introducing what homotheticity was, maybe over like short horizons or small technology shocks, homotheticity can be a decent benchmark, but you can get extreme departures from homotheticity with big enough changes. And a particularly extreme way you can get a departure is if when we're poor or when the tech is low, we consume some narrow range of goods. And then as we get richer or tech advances, we consume new goods. And so for like good N, we go from consuming 0 of it to a positive amount. And its growth rate is sort of infinite. So just to kind of illustrate what this changes, like how this changes your estimates and projections of long run growth, let's say X is a vector of goods. There's a continuum of goods from 0 to infinity, indexed by N. And you've got this this Kara looking utility function for each good N. So your utility ceiling, let's say you've developed goods from 0 up to 17. This is like a measure 17 set of goods. And you're not building any more varieties. What's your utility ceiling? What's the most utility you can possibly get with an infinite budget? 17, because you can get at most 1 util out of every variety if you consume an infinite quantity of it, in this case. Yeah, this is what I was just saying before. The goods are going to be gross substitutes at small quantities, but gross complements at large quantities. In fact, this is what you see, basically. So there's this rule of thumb called Marshall's second law of demand, that the elasticity of demand for a given good tends to rise with its price. And yeah, why is that predicted by a model roughly of this shape? Because when the price of a good is high, you're not going to consume much of it. And when you're not consuming much of it, you're really price sensitive. It's either you're not consuming any, or once it tips over into being worth buying the first unit, it's probably going to be worth buying the second unit as well. So when the price is high, you've got a really high elasticity of demand. And when the price is low and you're consuming a lot, you're going to have a low elasticity. This is kind of what that looks like. as we develop new goods, the utility ceiling rises in consumption per good. And I mentioned there's this paper called, it's still a working paper, I think, but it's called AI and Jobs, the Role of Demand, in which James Besson points out that, yeah, you can't just, that what AI will do to jobs, to wages, depends on how goods shares shift as we sort of automate and create large quantities of the things that machines can do. And he makes that hump point I was gesturing at before, that when you kind of look way back and you try to estimate the elasticity of demand for goods right as soon as they were introduced, you often see this pattern where the elasticity is really high when it's first introduced, and then it's low once it's mature. That's what I was saying about the Nordhaus point about different kinds of like IT. Yeah. Locally, things might be gross substitutes, but they often start out as gross substitutes. And on some level, they kind of have to start out as gross substitutes. Right. Because the price is falling and the share has to be rising from zero. Okay. Yeah, what would happen if you introduced a new good with 0 units yet produced and it was a gross complement to other goods? Well, then we'd sort of be infinitely badly off right then, because it would be like we introduced a third kind of shoe and and a third leg to go with it. And we suddenly have 0. We used to have lots of pairs of shoes and we suddenly have 0 triplets of shoes. So for simplicity, as I was saying, expanding varieties growth models overwhelmingly assume constant elasticity of substitution greater than 1, which implies that we can always make up for lack of new goods with lots of the old. And I think at least sometimes you want a model in which there's a utility ceiling with a fixed range of goods, which rises as the set of goods expands. Here's my horses point again. I think you can get on a higher utility level now than you could with infinitely many horses in the past, but a homogeneous of degree 1 consumption aggregate wouldn't allow for that. You'd always have to say that some future consumption bundle was equivalent to some large number of horses. So here's that first implication. And just the contrast with how it's typically framed, including by like Nordhaus in 1996, where he says, we're underappreciating the value of new goods, but the way he puts it is that there's an upward bias of prices or inflation over time. So the logic that people sometimes go with is, okay, well, we know what nominal consumption was in 1500. We know how many florins were exchanged for all the goods in Florence in 1500, and we know what nominal consumption is now. And if we're better off now than we used to think, that means that we have more real consumption now than we used to think. And so we have less inflation than we used to think. And so we just need to measure the inflation properly. But as the horse's point illustrates, there might be no inflation number that would kind of capture what's happened to consumption in a welfare relevant sense. Yeah, this also kind of helps to see what can go wrong with trying to chain weight, trying to come up with a number for how much growth there was over some stretch of time in which the technology changed a lot. You're going to get a finite, in effect, the number you put to how much growth there was from period 1 to period 2 will be an equivalent variation. You can say, how much would people have been willing to, like once you get to period 2, how much less consumption they've needed to be indifferent between period 2 with less consumption and period 1 as it happened. And you can ask the same question in the move from period 2 to period 3. Oh, I'm sorry, no, you can ask that would be the compensating variation. You can ask the equivalent variation. You can say, in period 1, how much more consumption would you need in period 1 with not much variety. To get you onto the same utility level as you wind up in period 2. And then once you get to period 2, you can say how much more consumption would you need to get you onto the same utility level that you get on in period 3. Those numbers can both be finite and you can chain weight them. But in period 1, when asking how much more consumption would you need to get onto the same utility level as you get to in period 3, this is above the upper asymptote that you can get onto in period 1. And so the product of these two growth rates will not be the answer that you would get if you tried asking the same question about the leap from period 1 to period 3 directly. Does that make sense? The second implication, which I'll show in detail on Friday, is that new goods can come to be bottlenecks. Actually, just like here. So this is that same example, right? So maybe that's what's happened. The reason why growth has slowed down isn't because we've sort of run out of technological ways to make manufacturing more efficient, but it's actually because of a good thing that happened. We came up with these services that grew more slowly, but which we wanted to shift over to. A lot of like common Twitter discussion about like how Baumol effects could slow growth even in the event of a huge surge in automation imply that the surge has to be incomplete. You know, like we'll just shift over to those few things that people are still required for. And that's what you would think if you were just thinking about like the fixed range of tasks, like task-based model that we were looking at before, right? Where like you can have Baumol effects, you can have, you know, growth bottlenecked by that little sliver of tasks that the water is needed for, right? But actually, the new goods don't even have to require labor to slow real GDP growth, right? Like if these services were provided by the robots and the manufacturing is provided by the robots, well, it could still be the case that the robots just happen to be getting more productive at manufacturing really fast and more productive at services really slow. So same thing, right? Income effect shifts us over to the services, and you can have the growth rate kind of change due to this income effect. So you can have Baumol even after the singularity of the goods we know about today. Yeah, an interesting thing is that because of this hump in the shares, where new goods have a low share of GDP, and goods that have been around for a long time, whose experience curves or whatever have driven down their prices a lot, also have a low share of GDP. It's always going to be intermediate quantity goods that sort of dominate real GDP. Does that make sense? Like in the Besson case, electricity will kind of rise and then fall as a share of GDP, or cotton, or whatever. So yeah, if just the way the experience curve works out, when the goods at an intermediate quantity, whatever the growth rate is when its quantity is intermediate, that'll kind of be the real GDP growth rate at any given time. So again, we can go into that more later. But the final implication of like taking new goods seriously that might be worth chewing on is that variety increasing R&D may itself come to be a bottleneck. So suppose that absent automation, when you allocate fraction S of the population to R&D, you get an instantaneous amount of technology. It's just the number of researchers to some power, that's lambda. This is kind of going to be like a steady state version of the Jones model. Like you're always immediately in steady state. And so if you have population growth at rate GL, A is going to grow at rate lambda GL, right? So you get, yeah, so we're kind of flattening the dynamic increasing returns to scale into a static thing. The exponents are adding up to 1 plus lambda. So now we have a Cobb-Douglas function in technology and goods. And so if we have like a budget of people to allocate between the research sector creating the A and the factories creating the C, or the production, I call it P here, then you're trying to maximize this, your consumption. And that's the same as trying to maximize some monotonic transformation of it, which is this, it's the same thing raised to the 1/1 plus lambda, but that's CRS, so it's more familiar. The optimal R&D share, assuming that like both kinds of people get equal wages, is going to be constant over time. So here you don't have a bottleneck. And the reason why you don't have a bottleneck is because technology and production are Cobb-Douglas. They combine in a Cobb-Douglas way to create consumption. So technology and the production of rival goods. So the assumption that technology is factor augmenting one way or the other turns out to fundamentally be the reason why the optimal R&D share is asymptotically constant in basically every standard growth model. Do you kind of see the intuition here? You've got resources, capital, labor, whatever, which you can create. You can either dedicate to production, or you can put those resources into creating technology. But if the technology is factor augmenting, on some level, you've got like a CES objective, and you've got like a budget of some resources. And the share you'll spend on one factor, the other factor in this Cobb-Douglas, are going to be constant over time. I'm trying to communicate the intuition by like making it a static problem rather than the dynamic one it is. But yeah. Oh, incidentally, this is another reason why we should expect that that lambda over beta, there's no beta here, but the lambda over beta governing the relationship between R&D and tech isn't so high. I think this is kind of interesting. So I was saying it's like a third. Bloom et al. Estimate it to be like a third. Well, what if it's higher? What if it's like 1? If it's 1, then on some level, we should be having half of people doing R&D. Because you have like RP, raise it to the 1/2. Sorry. But if technology and productive capacity are gross complements, you can't make up for a lack of technology with a lot of factories, because the factories are just creating things that you don't like that much after a while. If they're gross complements, then you're going to shift ever more toward the thing that's the bottleneck, which might be R&D if lambda is less than 1, or if it's harder to create technology than it is to create new factories. Sure enough, there's been this like long run rising R&D share throughout the developed world, rising or flat, but it's not really falling anywhere. And so just as you have this life and growth type argument, if you're familiar with it, that as we get richer, we might spend more and more of our money on medicine because we satiate in consumption goods. We shift over into like trying to buy more years of life. The R&D share could just rise and rise. And it could rise really quickly if we have like a huge growth explosion. R&D might kind of come to eat GDP. Those are some thoughts about product heterogeneity in a world of full automation and explosive growth.